in the next few video clips, we're going to be concentrating on waves and some of the key concepts behind them. Our goal here is to understand one of Einstein's two key postulates that he enunciated in his theory of relativity, and that would be the principle of light constancy, the other one, of course, being the principle of relativity. So the principle of relativity and the principle of light constancy. To understand the principle of light constancy, we need to know a little bit more about light, and light, especially as it acts as a wave, and thus we need to go over a few of the concepts dealing with waves. So we'll say a few words about waves here in this video clip, and then a couple more after this one. I've listed some of the key terms we'll cover here, so you can write those down if you would like as we go along here. Many of them you've probably heard before, but you may not quite be sure exactly how, exactly what is a wavelength, what is frequency, and so on and so forth. These are terms we often use in everyday language, or semi-everyday language, I suppose. But if you really had to define it, you might say, not quite sure exactly what that means. So we're not going to go into the whole long theory of waves, the different kinds of waves, and so on and so forth. We're just trying to hit the key concepts that we need to understand Einstein's approach here. So what I've drawn here is a typical periodic wave. A periodic wave is something that repeats its pattern. In fact, we could say, for our purposes, a wave is a disturbance in a medium that propagates along, or propagates through that medium, travels through that medium. Classic example, of course, would be water waves. And we could imagine, for this situation here, let's say we had a tank or something like that, or pond, whatever you want to imagine. And the dotted line here represents the normal still water level, the water level when nothing is happening. And then maybe we put our hand in there or have some sort of device where we can start moving it up and down, creating the ripples, creating the waves that will then travel, propagate outwards from our source of disturbance. So that would be our wave source, just our hand moving up and down, creating these waves going out, and we will draw the situation such as this. Obviously, we really need to do it in 3 dimensions, and it get a little more complicated, and the waves might die out as we go along. But we're imagining an idealized situation here, as we often do in physics. And so this would be the peaks and troughs of the water wave as it propagates along. So here would be the still water level. It goes up, and then you have a trough, and up and down, and up and down, and up and down, and so on and so forth. So again, a couple of key concepts here. There is a medium involved. Okay, in this case, the medium would be water. It could be something like, you can imagine waves traveling as vibrations through a steel rod or steel bar, something like that. We talk about sound waves, of course, a disturbance or a pattern traveling through the air or a type of gas. And really 2 terms that we won't need, but you may have heard about: transverse and longitudinal. Transverse waves are where the disturbance is up and down, transverse. So if this is water here, the water molecules actually are moving up and down, up and down, up and down. And so that's a transverse type of wave where the wave motion is up and down vertically here. A longitudinal wave is where the medium, whatever the medium is composed of, in this case we'll do air, the motion is back and forth. For sound waves, actually, you have areas of higher density, where the air molecules group together more, and then areas of lower density. So this would be high density area, lower density, high density, lower density. But it's the movement of the medium, the air molecules in that case, are back and forth this way in the direction the wave is going. So it's longitudinal with the wave. And so there are certain concepts like that in terms of different types of waves, transverse, longitudinal, and so on and so forth. We won't actually need that, but you may think, water waves and sound waves, they are different. This is one of the ways they are different. Okay, so we're going to talk about essentially transverse waves, because light waves are transverse waves. So we'll learn about it a little bit later on, not in this video clip, but in a later video clip. But let's get some of these key concepts down. Again, a medium is involved. So in this case, we're going to imagine it's water. A periodic wave is something where the pattern or disturbance repeats itself. You have peak and trough, peak and trough, peak and trough. And again, we're just assuming that it doesn't die out or anything like that. It just continues on like that. So it's a periodic wave. Some other key concepts, the amplitude of the wave. The amplitude of the wave, as maybe you might guess, is just the up and down distance, measured usually from the center still point, as it were, if we're thinking about our water. So the amplitude in this case would be this distance there, or that distance there. Okay, so a wave with higher amplitude means you got higher up and down motion of the water molecules as the pattern, the disturbance goes along. The wavelength, the term we've all heard, but what exactly does it mean in this case? The wavelength is a distance, and it is essentially the distance, the easiest way to think of it is the distance between two peaks. So, for example, from here to here is going to be the wavelength. The wavelength. And a symbol, we won't really have to use these symbols too much, but if you've had a little physics before, you may remember a common symbol for wavelength is the Greek letter lambda, lowercase lambda there. So that's the wavelength. Technically, the wavelength is the distance between any 2 points that are on the same part of the pattern. So we could also measure the wavelength from this point to that point. And if it's truly a periodic wave where everything is just repeating itself, exact same situation, then this distance here between those 2 points is the same as the distance between 2 peaks, is the same as the distance between, say, 2 troughs there, the negative peaks, and so on and so forth. So that's the concept of a wavelength. So when we talk about a short wavelength wave, it means it's compressed more. You have more oscillations up and down within a certain length, say 1 meter or 1 foot or whatever you want to measure with. Okay, so a short wavelength means you have more of these up and down oscillations in a given length, because that means the actual distance between 2 peaks is going to be smaller then, if you can get more of the up and down oscillations in a certain distance. A long wavelength wave is going to be something where, just the opposite. It's going to be farther distance, longer distance between the 2 peaks or between the 2 points on the wave. So short wavelength, long wavelength. What about then the period? The period, now we're imagining here that, again, some of you who may have taken physics before know there's such things as standing waves. If you can get them going in your bathtub maybe, or on a string, waves on a string, where they just sort of look like they're stationary and not doing anything. And in this case, so we're going to assume our waves are traveling waves, so the disturbance is actually traveling along here. You can see the waves flowing through the water, as it were. And so the period then is as we're watching, let's just say this is our reference point right here. So here we are, standing right here, and we're watching the wave travel by us like that. And the period then, we have a little stopwatch, the period is going to be the time it takes from one peak until the next peak gets to us. Okay? So often measured in seconds, but any unit of time. So the period is going to be measured in seconds, or minutes, or hours, or years, or whatever you want, but often in seconds. Okay? So that gives you an idea, really, of how fast sometimes the wave is traveling, depending on a few other things as well. But that's the idea of the period. So period is measured in, we'll just say it's measured in seconds, really, or as I said, any unit of time. So wavelength measured, we'll say wavelength is measured in meters, centimeters, millimeters, nanometers if you want. Period measured in seconds. Now, another concept is the frequency. Okay? The frequency, in fact, often the period, I said we use the Greek letter lambda for wavelength. Often the period we use just a capital T for, since it's measured in seconds. The frequency is, if you think about it, you think, oh, what's frequency? How frequent is something? Okay? Well, what that really is saying here is how frequent are the up and down oscillations? That's what frequency means in the context of a wave. How frequent are those up and down oscillations? How fast are they occurring, in a sense, as this wave goes by me? So a high frequency wave is going to be one with a lot of oscillations in 1 second. Say I'm here and I'm counting the number of oscillations per second I see, the number of up and down movements that my wave is making as it goes by. If it's a lot of oscillations in a second, then I say that's a higher frequency wave. If it's fewer oscillations in a given time period, in a second or whatever it might be, that's a lower frequency wave. Okay? And in fact, frequency, I'll just put over here, frequency, we'll use the lowercase letter f for, although sometimes in your physics textbooks, again, if you've had physics before, another common letter is the Greek letter nu for that. We'll just use f, though, just to remind ourselves for frequency there. And it turns out, if you think a minute here, there's a relationship between period and frequency. Okay? Let's think about that a minute. So we said the frequency is how many up and down motions we get, how many oscillations we get in 1 second. Okay? The period is how long it takes between peaks. So if I have a high frequency wave, right? So a high frequency wave, meaning I have a lot of up and down oscillations per second, it means the distance between peaks must be pretty short. The period must be small. Must be a small number if the frequency is high. And if the frequency is low, meaning I don't have as many oscillations per second, that means the period must be longer. There's a longer time between each peak, and so I'm not getting as many oscillations per second. And in fact, there's an exact inverse relationship between period and frequency. We can write period equals 1 over the frequency. So that if the frequency is a big number, if we talk about a high frequency wave, or really a high frequency anything, it means that the period is going to be very small. Got a big number down here, 1 over a big number makes this a very small number. On the other hand, if I say I have a low frequency something, like a low frequency sound, right, coming out of our bass speakers or whatever, this number is going to be much smaller. 1 divided by a small number gives me a bigger number over here in general. And so the period is going to be longer then. So high frequency, short period, low frequency, longer period. There's also a relationship between, for certain kinds of waves, like periodic waves we're talking about here, between the wavelength and the frequency and the velocity of the wave. We're not going to try to prove this or anything. We're just going to state it as a fact. And that is, if I've got a certain velocity, okay, so we'll call v the velocity of the wave here. It turns out that if you say, okay, here's a nice way to think about things. Think about the units of things. When you're trying to remember a relationship like this, it's going to be a very simple relationship, we'll see, but it's easy to sort of get it flipped around or the wrong way. And so think about the units involved. You say, okay, I'm told, or at least I know, that, I know, or at least I'm told, that there's a relationship between wavelength, frequency, and velocity. Okay, so velocity, I know, we'll say is in meters per second for our units, a length divided by a time. Frequency, note that if period is in seconds, frequency has to be inverse seconds. Okay, because they're inverse concepts, inverse relationship here. So frequency has units of 1 over seconds, or sometimes we say that, we write it like this in just sort of a little exponential notation, inverse seconds, but 1 over seconds, because it's the inverse of period. And wavelength, remember, is a length, as the name implies. So lambda is meters. Okay? So given those facts of what the units are for each of these, what the dimensions are, dimensions of distance over time, or inverse time, or distance for each of these, and we're told that there's a simple relationship between them, let's just think about this a minute and say, well, velocity is meters per second. Look what happens if I take the wavelength and multiply it by the frequency. I get meters per second. I have meters times 1 over seconds and that gives me meters per second. In fact, that is the relationship here. We'll write it down here. A little more room. The velocity, this is for our periodic wave here, and technically even there's such a thing called harmonic wave. Again, for those of you who might have had a little physics before. If you haven't, don't worry. We're not going to have to use that concept. We just want to get the basic concepts of waves here. Velocity is going to be lambda, the wavelength, times the frequency. Because velocity is meters per second. Lambda is in units of meters. Frequency is in units of 1 over seconds. Instead of 5 there, S down there for seconds. Okay, just make that clear, that S being our abbreviation for seconds. And so this is just meters per second. And this is the relationship right here. So this is the key relation. The velocity of the waves we'll be talking about is simply the wavelength times the frequency. And so know what happens here. If lambda gets big, let's say for a given velocity. So say we have a given velocity wave traveling along. If lambda is big, that means frequency has to be smaller, to make this work, and so on and so forth with that. You can go the other direction too. You can have a high frequency wave. Big frequency means short wavelength. Okay, short wavelength, big frequency. So small wavelength, big frequency. Or big wavelength, lower frequency. Let's use the terms right. So low frequency, big wavelength, short wavelength, high frequency. Okay? And we'll mention those a little bit more maybe when we get to the light here. But those are the key concepts of our waves now. A few words about waves, just what wavelength is, the whole concept of a wave as a pattern, a disturbance propagating through a medium, and again, water is a classic example that we can use for that. And then just some of these simple relationships with waves between velocity, wavelength, frequency, and of course we could put period in here as well. Lambda times frequency is the same thing as, so we could say also, V equals lambda divided by the period is another way to write this, because instead of frequency here, period is 1 over the frequency. Frequency is also 1 over the period, the other way around. And so we can just mix and match those relationships as long as, of course, we're doing it the correct way and have the units right there. Okay, so that's a few words about waves. We have a few more words to say about waves in the next video clip when we get into the concepts of phase and interference. So we'll do that next. Continue on with our few words about waves, part 2. We need to talk about a couple of key concepts here. One known as the phase of the wave, and leads us to the concept of interference and constructive and destructive interference. This is going to be key, as we'll probably talk about actually in the next video clip, with a famous experiment that was done a few years before Einstein's time that really put a wrench in the works for physicists. They could not figure out what to do with the results of this experiment. And it was called the Michelson-Morley experiment. So we're leading up to that, getting the concepts down. We need to understand not only Einstein's principle of light constancy, but also how to understand this so-called Michelson-Morley experiment. And interference will be a key concept there. So let's take a look at it. Let's say we have two waves. We can imagine they're water waves. Again, later on, of course, we'll be imagining they're light waves. Either one will work in this case. And so here's wave number 1. Here's wave number 2. The concept of phase means that as you compare them, say they're traveling along side by side here, then they're in sync with each other. The peaks match up, the troughs match up. And in this case, pretty much exactly. So we'd say those two waves are in phase with each other. In a minute, we'll do an out-of-phase situation, but you can probably guess that just means then things don't line up if it's out of phase. And then you can also ask the question, well, how much out of phase is it? Well, let's do the in-phase case first. So we've got our two waves, the way I've drawn them, more or less. limits my artistic ability here a little bit, but try to get them synced up. So the peaks and troughs are all lined up together. And so again, imagine two waterways maybe traveling side by side or maybe just angled slightly so they're about to come together. And what will happen is if they're in phase with each other, if the wavelengths are the same and the frequency, the period, and everything is in sync, as it were, the peaks and troughs are in sync with each other. As they come together here, the waves are going to combine, and the peaks are going to get even higher and the troughs even lower. In other words, what happens is the peak parts add, the trough parts add in a sense, and everything else adds along here as well. So the combined wave then is going to look something roughly like this. We're going to, if these are the same height, the same amplitude, we're going to double it then. So it might look something like way up here, and then way down, and way up, and way down, and way up again, more or less. And if we draw the center point line there, not quite, in terms of my diagram here, maybe not quite exactly double, but that's the concept, that the two peaks add, the troughs add, and so the amplitude increases then. Remember, the idea of the amplitude is the distance from the highest peak to the center point there, or also the lowest point there. And so this is known as constructive interference. The waves are interfering with each other, coming together, they're adding together, but they're doing it constructively. Okay? In other words, the peaks add, and you get bigger peaks, and the trough sections add as well, and you get deeper troughs that way. So that's known as constructive interference. And so, again, in a bathtub situation, a water tank, or a swimming pool, something like that, if the waves are in phase with each other, they start adding together, you get even bigger waves going on that way. And for light waves, you get brighter spots. You get an increase in the intensity of the light. So that's constructive interference. What about destructive interference? So let's do that situation here. We'll get rid of our combined wave. And actually, we're going to get rid of wave number 2. We need a different version of the wave. In fact, before we get rid of it, let's just think about what's going to happen. Now we're going to draw the second wave so it's out of phase with the first wave. Our first example here, they're both in phase. In fact, exactly in phase with each other. So everything added together. They combine, we get constructive interference. Now we're going to draw it the second wave so it's exactly out of phase with it. And in the terminology, again, for those of you who might have had a little physics before, maybe even just heard it, because it's sort of a common term. It's 180 degrees out of phase. Why it's 180 degrees, we won't go into that, but you may have heard that term before. So it's exactly out of phase with it. So wave 2 then is going to look something like this. Where we have peaks, we're going to have troughs. Where we have troughs up here, we're going to have peaks. And so if I can channel my, I don't know if this would even be anything close to Picasso, but let's see, I'm already off here. Try this again here. Okay, something like that. Maybe a little too big in terms of some of my troughs here, a little too deep. Okay, so hopefully you can, in your mind, fix all the inconsistencies there. But the big thing we're after here is we see the trough of this wave is matched up with the peak here exactly. The trough here is matched up with this peak, trough, peak, and so on and so forth. So now you imagine these two waves, again, water waves maybe traveling next to each other, coming together to an intersection point up here. If they're exactly out of phase, when this one has a peak coming in, this one's going to have a trough, and they cancel each other out. And you get just still water at that point. And if you have a trough here, but a peak is coming in here, they're going to cancel each other out, and you get still water at that point. So when you have destructive interference, when the two waves are exactly out of phase with each other, the combined wave is simply this. I think I can handle drawing that, more or less straight there. Okay, so destructive interference, you end up with no wave at all. You had two waves coming in, and again, we're assuming that the wavelengths of the two waves are the same, so everything matches up nicely, and so on and so forth, and the amplitudes are the same. and everything cancels out exactly. Now you might say, well, what happens if the amplitude of wave number 1 is greater than the amplitude of wave number 2? So in other words, this peak is bigger than that trough is deep, or this trough is deeper than that peak is tall. Well, you'll still get destructive interference, but this wave will not completely cancel out that wave. And so you will be left with a little wave after that. You won't be left with nothing at all. Okay, so that's the concept of destructive interference, constructive interference and destructive interference. And as we will see, as I mentioned a few minutes ago, this is going to be the key concept in understanding the Michelson-Morley experiment, and then beyond that, understanding why it was such a big deal for the ideas in the special theory of relativity and what effect it might have had on Einstein himself in terms of his thinking about the special theory of relativity. Okay, so that's a few more words about waves, part 2. In the next section, we'll actually have even a few more words about waves, so we'll get on to that in just a few minutes. So on to part 3 of our few words about waves, although at this point you may be thinking it's a little more than a few words. What we need to do that now, though this is really the last part of our 3 parts here, we want to talk about 3 key facts about the speed of waves. Before we do that, though, just as an aside, in the last video clip, offhand, I mentioned Picasso. It's interesting for those of you who are fascinated by art history, things like that Einstein and Picasso were contemporaries. And in fact, there's a book, for those of you interested perhaps, called Einstein, Picasso by Arthur I. Miller. That you might want to check it out, see what it's all about. The subtitle is Space, Time, and the Beauty That Causes Havoc. So it sort of puts them side by side, looks at their life and their work together and draws some parallels and things like that. So Arthur I. Miller, Einstein, Picasso. I just happened to be thinking about that since I mentioned Picasso offhand last time. Maybe that's why I did subconsciously. I was thinking about that. I'm not sure, but there you go. Einstein, Picasso, Arthur I. Miller. As you may know, there are dozens, hundreds of books on Einstein out there, and many of them are very good. So you can explore that. Later on in the course, we'll talk about some books to continue on with in terms of Einstein if you're interested in pursuing it more. But now we're on to a few more words about waves. Part 3, key facts about the speed of waves. I think I mentioned this in an earlier video clip, but just to make sure, we're using speed and velocity interchangeably. For those who've had a little physics, you know technically there's a difference between velocity, the concept of velocity, and speed being the magnitude of velocity. Velocity having a direction as well as a magnitude. So again, we're not going to have to be too concerned about those exact definitions. So we'll say speed of waves, velocity of waves, speed of light, the velocity of light will be meaning the same thing. Okay, so 3 key facts. Number 1 key fact is the speed depends on the medium. So what do we mean by that? Well, consider waterways. Again, maybe we have a long tank. We're going to generate some waves in this tank with our hand or some sort of paddle device. If we replace the water in the tank with another type of fluid, another liquid that had different properties, in particular had maybe different viscosity, different density, the speed of the waves we can generate is going to be different compared to the water. At a certain point, if you have molasses in there, you can't generate really waves at all, or they'll die out almost immediately. But the idea being is that the speed of waves, this pattern disturbance propagating through a medium, is going to change depending on the medium itself. Another example would be vibrations, which a wave-like phenomenon in a steel bar or something like that. The more rigid the steel bar is, the faster the waves are going to travel, everything else being equal. If it's a softer type of bar or whatever, then the waves are not going to travel as fast. So, key point, the speed of the waves depends on the medium. Second point is, if we have a moving source, we're going to add on to this in a second here. What do we mean by moving source? Well, again, go back to the idea of a tank, long tank of water maybe, and we have a pedal device or a hand. We're going to generate waves by just moving it up and down. And one key thing to remember, I mentioned this actually I think in part 1 of the video clip, but remind ourselves here is that when we're talking about, if we have this paddle device and we're generating waves and they're traveling down our tank or through our bathtub or swimming pool or whatever it happens to be, the water molecules themselves are not moving with the waves. The wave that's traveling is a pattern or disturbance within the medium, which is the water in this case. The actual water molecules are moving up and down in that peak and trough. So say we've got some water right here. I start generating my waves. So the water molecules at this point, as a peak comes, they're going to move up. And then the trough, they're going to move down, and then up and down. So the water molecules are moving up and down, and the wave pattern is traveling that way. So we're not actually talking about the speed of whatever the medium is composed of as it's moving through. It's the speed of the pattern or disturbance moving through the medium. So then when we have a moving source here, okay, so I've got my paddle device moving up and down, instead of having it be stationary and watching the waves go along, and maybe I'm outside here measuring the velocity of the waves, I'm going to start moving that paddle device. So let's think about what's going to happen here. We've said that the speed of the waves depends on the medium. By moving the paddle device, I'm not changing the properties of the medium in any way, unless I move it up and down so fast it starts heating the water or something like that. But we'll assume we're not doing anything like that. So the waves are just going to keep the peaks of the waves. Imagine the peaks of the waves going out here. As I move the paddle device along, that means I'm generating a new peak before this peak has traveled as far as it normally does. So what happens is the peaks as I move along here are closer together than if the paddle device was just normally stationary like this, generating the peaks that go by. So in other words, generate a peak, it gets to here, and normally the wavelength would be that long if the paddle device is not moving. But in this case, I've moved the paddle device a little bit more over this way as the wave has traveled out. And now I'm generating a new peak right here. And so that distance is shorter just because I'm moving the paddle device, the source of the waves, along. So the peaks going in this direction sort of bunch up a little bit. And actually the peaks, if we extend our tank the other direction as well, the peaks are going to extend out a little bit more. So imagine a paddle device in the middle where I'm generating waves going in both directions. If I don't move the paddle device, everything's the same. If I start moving the paddle device in this way, the peaks are going to be bunched up a little bit more, and over here they're going to be spread out a little bit more. So in this direction, I'm shortening the wavelength a little bit. In this direction, I'm extending the wavelength a little bit. So when I have a moving source, just to emphasize here, no change in wave speed. Okay? There's no change in the wave speed because the medium, properties of the medium are not changing. What is changing is the wavelength. Okay? And we're dealing in just a simple basic case here, leaving out a lot of complicating circumstances. But essentially, here's my wave generator, my paddle device. As it moves this way, the distance between the peaks gets a little shorter, and they get spread out this way. So in this direction, the wavelength is shorter, and it's longer out this direction. Well, remember the relationship we had from part 1 of our few words about waves? We said the velocity of a wave, the waves we're considering at least, is the wavelength, lambda, times the frequency f. Now, we've just said that we're not changing the properties of the medium, so the velocity of the waves is going to stay the same. What we're changing in this case with a moving source is the wavelength. In this direction, as I move the paddle device along, the peaks are closer together, which means the wavelength is a little shorter. In this direction, away from the paddle device, it's moving away from the circuit, peaks are a little bit farther apart. Wavelength is longer. What does that imply about the frequency? If the wavelength is getting shorter, in order for the velocity to remain the same, the frequency has to be higher. Let me do an example. Let's just say this is 24. Say velocity was 24 meters per second, right? And I said the wavelength was 4 meters. Frequency was 6 inverse seconds, really. Some of you may know that the units of frequency are hertz. So when we talk about megahertz, that's millions of hertz. So we won't worry about the details here, but just the idea. 4 times 6, 24 obviously. So now I'm saying as a paddle device moves along here, the wavelengths are getting shorter. Let's say they go from 4 to 3. So that means the frequency has to increase. So I'm going to have a situation where it's 3 times 8. That's why I chose the numbers here, so I could do it easily. So 3 times 8 is still 24. Right? So the velocity stays the same. The wavelength has compressed a little bit, gotten shorter, so the frequency has gone up. And whether you realize it or not, you probably have encountered this in real life, or at least seen it in the movies. Think about a train whistle, right? If you have a train whistle and the train is coming towards you, you have sound waves coming toward you from the train whistle. The velocity of the train is a moving source, or the train is a moving source with a certain velocity towards you, the source of the sound waves. As we've been talking about, the velocity of the sound waves toward you does not change. They are still coming towards you at the same rate. They won't get there any faster to you. But because it's a moving source towards you, the movement of the train compresses the wavelengths of the sound out in front of it as it travels away from the front of the train. And that means shorter wavelengths, higher frequency. So that's why when the train whistle coming toward you, you hear it, it's a higher pitch. Then as it passes by you, now you're behind the moving source. Okay, just on my paddle device, I was moving the other direction though. So the paddle device was moving this way. Shorter wavelengths here, longer wavelengths behind it. Same idea for the train whistle, whether it's moving this way or that way. It doesn't really matter. We're pretending it's coming this way. So here comes a train toward you. It's compressing the sound wavelengths in front, which means a higher frequency, higher pitch sound. As it moves by, what you hear, the pitch drops. It goes like that, more or less. And that's because behind the source, the moving source, as it moves away from you, the wavelengths spread out a little bit, meaning that you have a bigger wavelength. Okay, this number becomes bigger. The frequency, therefore, has to be smaller to keep the velocity the same, the whole thing the same. And therefore, you have a lower pitch sound. And some of you, again, may know that this is something called the Doppler effect. Doppler effect. So it's just a little side noted, actually. There is a so-called relativistic Doppler effect. We're not going to get to that in this course. But it is important. The important point here is that wave speed depends on the medium. When you have a moving source, it does not change the speed of the wave through the medium. It changes other things. It changes the wavelength and frequency. Does not change the speed of the waves. And this is important. You may say, well, why are we doing all this with wave stuff? It's important because we mentioned Einstein had two postulates, two principles that he enunciated in his special theory of relativity. One of them was the principle of relativity. The second one was essentially number 2 here, our number 2. He called it the principle of light constancy. And essentially it was that a moving source, there's no change in the wave speed. And light was recognized as a wave. So he said, hey, with a moving source, there's no change in the speed of light. But what then became very interesting was he combined the principle of relativity with his principle of light constancy and got very strange results. And that's where we're heading to in, not quite yet, but we're heading in that direction over the next week or two. So that's why this is so important to understand. A moving source, no change in the wave speed, because it's going to help us understand what Einstein was doing when we get there. Okay, moving source, no change in the wave speed. One other key fact, though, a moving medium. A moving medium, what do we mean by this? Well, again, let's go back to our water tank. So here's our water tank here. And we have our paddle device generating waves flowing down the tank. And we're measuring the velocity of the waves there. And as we just finished saying with our principle number 2, if I move the source of the waves through the water, it doesn't change the velocity of the waves. You know, the frequency and wavelength change, but not the velocity. But now let's think of another situation. Here's my paddle device, here's my tank, and I'm measuring the speed of the waves as they go along. What happens if I move the whole thing? So in other words, the medium is moving as well as the waves. In that case, when I have a moving medium, the velocities do add in a sense. Okay, so I'm measuring, before I set the whole thing in motion, I'm measuring the speed of the waves as they go along here. And then, maybe I have it on rollers or something, on wheels, I start moving the whole thing. And then I measure the speed of the waves going by me. And pretty intuitively, intuition is correct here, you'll see the speed of the waves increase. They'll be going by you at their normal speed, plus the speed that the whole thing is moving by you. So with a moving medium, then the wave speed, we'll just say the wave speed changes as an observer is measuring it. Now, in terms of the medium here, another way to think about this, we've done our water tank example, but it's also the difference between, say, generating waves in a pond or a lake and a flowing river, right? So, if you're able to set the lake in motion in a sense. So if it's in the lake or pond, again, it's just you generate the waves, they're flowing along here. If you have that same situation in a river, and let's say the river is flowing this way, so I'm generating my waves here, and they're traveling along, but then everything is in motion as well. All the water molecules and everything are flowing this way, and so that adds velocity to the velocity of the waves if I'm on the bank measuring those waves go by. Or, intuitively also, if I'm going upstream, up against the current, right? So I'm watching the device here, maybe on a boat, as it goes up the current, generating waves. The flow current of the water will retard the velocity of the waves trying to go upstream. Again, that's one case where our intuition actually is correct there, that the wave speed will change. If the whole medium is moving, the wave speed will change. Why is this important for our purposes? Because in the next video clip, we're going to talk about something called the luminiferous ether, and that is the supposed medium for light waves. And Einstein actually got rid of it later on. We'll see how that happened. But there are two key experiments that we need to talk about, because one of them, known as the Michelson-Morley experiment, gave one result in terms of how the ether worked and how light waves traveled in the ether. And a second experiment involving something called stellar aberration, stellar meaning stars, and aberration, we'll figure out what that means, gave an opposite result, a result that contradicted the Michelson-Morley experiment. And both of them were well understood. And so it was like physicists were just nonplussed. They couldn't figure out, what do we do with this? How do we understand this? And they came up with a number of very innovative ideas, very creative ideas, but it was still a big mess. And they tried and tried and tried, and eventually that was one of Einstein's great triumphs. By attacking it sort of from a different perspective, he was able to show that these things actually were not in contradiction, even though they seem to be. But by coming from a perspective where they're not in contradiction, then you get all kinds of other interesting and weird results. So that's where we're heading with this. These principles are going to be key in understanding these two different results, the Michelson-Morley experiment and stellar aberration, and so we'll be covering those over the next few video clips.